This conference will now be recorded.
Very good morning, students. Today we'll discuss numerical problems from the paper JEE Mains paper 2021, 31st August, shift 1. So let us start our discussions. The first question says a uniform heavy rod of weight 10 kg meter per second square. That means the weight itself. Okay, this is weight itself, 10 kg meter per second square. Cross sectional area 100 centimeter square. Length 20 centimeter is hanging from a fixed support. Young modulus of the material of rod is 2 into 10 to the power 11 Newton per meter square. Neglecting the lateral contraction, find the elongation of the rod due to its own weight. So let me draw the figure. There is a uniform rod and it is said it is heavy. The rod is heavy, actually heavy uniform rod, and it has cross sectional area A given as 100 centimeter square. If we require in meter square, we'll get 100 into 10 to the power minus 2 whole square. That means 10 to the power minus 4 meter square. So area will be 10 to the power minus 2 meter square. Okay, and the length, see, length of this is, original length is L. Okay, original length is L, and that is given as 20 centimeter. Okay, if we require, we can find out the length in meter like this. Young modulus is given. You have to neglect the lateral contraction. Then what will be the elongation due to its own weight? So first of all, since it is heavy and it has weight, when you hang it vertically, due to its weight there should be some elongation. So that elongation you have to find out here. See, first of all, you have to understand that this is uniform rod. So center of mass will be somewhere at the middle. So center of mass will be at the middle, and as you know, center of mass means the whole mass of the rod. Let us suppose the mass is capital M. The whole mass of the rod will be concentrated at this particular point. Okay, since it is uniform rod, we can take this. All right, so we can think now this rod as a rod of length L by 2, right? Kind of that you can think, because the center of mass is situated over here. So you have this thing. Now you have to find out what is the elongation. See, for that, let me find out the expression for the Young modulus, that is stress by strain, that means force per unit area or force by area that is stress, by strain. Strain is delta L divided by the original length L by 2. See, the length is L, but I have to take the length up to which, like where the mass is situated, that is L by 2. So that's why I'm taking this. And look what I'm writing. Instead of writing F, I'll directly write W. Okay, so L will go, and you will have here 2 into delta L into A. I hope you understood this. Okay, now I have to find out what is this delta L. Let us find out. Delta L will be weight into length divided by 2 into area into the Young modulus. Now it is very simple. If we put the values, we will get that. Okay, this is 10 kg meter per second square, and length is how much? Length is 20 centimeter, so that is 0.2 meter, right? 0.2 meter divided by 2 into area. Area is 10 to the power minus 2 meter square, and Young modulus is 2 into 10 to the power 11 Newton per meter square. Okay, now look, this 10 and this 0 will cancel each other, so you'll get this. See, then what we get, this is 10 to the power 8, sorry, 10 to the power 9, so 10 to the power minus 9 will go in the numerator, and this divided by 2. 2 means 0.5, so look what I get, delta L to be equal to 0.5 into 10 to the power minus, this is 10 to the power minus 9, 10 to the power minus 9, so I can write 5 into 10 to the power minus 10 meter. Okay, all right, so see the option D. Option D will be the correct answer for this question. So here the key concept is that, see, let me write in red ink. So the key concept here is the length. You take initial length. Okay, the key concept is the initial length. Initial length, actually that is the, the position of the position coordinate, that is actually the position coordinate of center of mass you have to take from the fixed point. Position coordinate of COM. Okay, this is what we have to take. All right, we'll go to the next problem. Okay, this is also a very interesting problem from the projectile motion. So the question says a helicopter is flying horizontally with speed v at an altitude, that means height h, has to drop a food pocket for a man on the ground. You can see that. So here is the helicopter. Okay, here is the helicopter. Anyway, so you can just think of helicopter which is dropping a food item for a man on the ground. So at this particular height, the so the food item is being given like this. Okay, I think see, this is not thrown, this is just dropped. I'm sorry, just dropped. Drop means, you know, when the helicopter was here, just dropped. That means with no initial velocity in the vertical direction. So this is the main point you have to understand, that when the helicopter is moving with speed this much v horizontally, it doesn't have any vertical velocity, and the food pocket is just dropped. It is not thrown, it is just dropped. That means initially there is no vertical velocity. So no vertical velocity. Okay, no vertical velocity. So this is the main point. Now let us see this altitude h, you can see that. So what is the distance of the helicopter from the man when the food pocket is dropped? Okay, so distance means this one, you have to find out this one. Okay, let us say this distance is small d. You have to find out this small d, this distance, okay, from the helicopter to the man when it was dropped. So how do I find out? So you can see from this figure itself, if I know this and this from the Pythagoras rule, we can find out what is this hypotenuse. This is kind of a right angle triangle, right? The height is known, and answer is like options are in terms of h also. But this r, this range from this particular position where the where the helicopter was and where the food pocket lands. Okay, that is in the hand of the man. So this distance you have to find out, this range you have to find out in terms of v and h. Okay, so how do I do that? I know initial velocity was 0, like in the vertical direction. Initial there was no velocity, right? So can I find out what is the time it takes to come to the rest? Since the motion is purely motion under gravity and free fall, I can find out what is the velocity as well. So velocity means a half mv square is equal to 2gh, kind of that, right? So the point, at the point where, okay, this I don't require, I'm sorry. No, it is required. Let us find out anyway. So you know this, no, this is actually, yeah, half mv square. I need actually the velocity, final velocity, or even that is not required. We need to find out what is the time it takes to land. Okay, that is the time of flight. I need to find out so that we can find out. See, the velocity initial, this velocity anyway is v into t, right? This v, see in the option v is there, so I no need to find out any other velocities, etc. So what is the main requirement? That is the time of flight. By the time the food item has gone up to here. So what is time? So I can find out h is equal to ut plus half gt square, right? Ut plus half gt square. If I just consider the motion, vertical motion, g I'll take positive for the time being. Otherwise, I have to take this height minus. Anything is fine. Half gt square. Initial velocity in the vertical direction is 0, right? So I'll get this as 2gh and square root of that, right? So I have got the time of flight. Then what will be the r? R will be v into this time. So I can write, see this t is this one. So I'll just keep everything inside the square root. Then see 2g root 2 square root of 2gh and v square. Okay, this is actually the range. Okay, now I have got this r. So I have to find out d. So d will be square root of h square plus this r square. Okay, so what is this r square? R square is actually 2gh v square. Okay, and then h square. So this is actually the answer. So the option B, I'm sorry, I think I have, do I have something missing? 2h v square by g. I should get that. Half gt square. I see. This is actually not 2gh. I'm really sorry. So 2h by g. I'm sorry. This is actually 2h by g. So 2h by g. This will be g in the denominator. Okay. So 2h v square by g plus h square. 2 v square h by g plus h square whole inside the square root. I'm really sorry for this silly mistake. So I hope you have understood the concept. You can just carry out the calculation properly, and you will see this option C will be the answer for this question. Okay. All right. So we'll go to the next problem. Okay. This is again a very interesting problem. The problem says the masses and radii of Earth and Moon are m1, r1, and m2, r2. I'm sorry. Let me change the ink. Okay. So the masses and radii of the Earth and Moon are m1, r1, and m2, r2 respectively. Their centers are at a distance r apart. Find the minimum escape velocity for the particle of mass small m to be projected from the middle of these two masses. Okay, so see, I have Earth and Moon. So let us say this is Earth. This has got radius r1 and mass m1. Okay, and I have got Moon. Okay, it has got r2 radius and mass m2. Now their centers are separated. The centers are separated by a distance r. So centers are separated by a distance r. That means the whole this distance is r. Okay. Find the minimum escape velocity for a particle of mass small m to be projected from the middle of these two. See, the middle point would be somewhere here, which is, see, from here it is r by 2. From here also it is r by 2. From the center of the earth, this is r by 2. Right. Very nice. So far it is all right. See here, there is this mass, small mass m. I have to provide escape velocity okay, to this object, so that it goes to infinity, okay, goes to infinity. So here you can see this problem can be solved simply by the conservation of total energy, simply using the principle of conservation of total energy. So what is that? Total mechanical energy will be kinetic energy plus potential energy. That's all. Okay. So let me tell you one thing here. When an object is given escape velocity, it will go to the infinity. And at infinity, what will be the velocity? That will be zero. What will be the potential energy? That is also going to be zero. So kinetic energy plus potential energy both will be zero at infinity. For gravitational potential energy at infinity will be zero, and also the kinetic energy at infinity it will be zero. So I have got one thing. Let me tell you this point. Let me just take this point to be P. So I have to give an escape velocity to an object which is at P point such that it goes to infinity, where there is no potential energy as well as kinetic energy. So first of all I have to find out, so here the problem is the application of, so applying conservation of principle of conservation, principle of conservation of mechanical energy, ME. Okay, so initially at this point, see what will be the potential energy and what will be the kinetic energy. Let me give velocity u, sorry, v e, escape velocity. So what will be the kinetic energy? Half m v square, right? And what will be the potential energy? Gravitational potential energy will be negative always. So what will be the potential energy? So potential energy is the energy due to attraction or due to interaction. So here there are two objects. See M1. See there is earth which can interact or which can pull towards itself, towards its center, and there is moon which can also pull these objects of mass. There will be potential energy due to both of them. So what is the potential energy? Mass into potential. Potential is, we know potential Gm. So for the earth, G m1 by r. What is the distance? See r2, right? See r by 2. I'm sorry, this is r by 2. R by 2, right? So Gm by r by 2 into m. So Gm1m by r by 2. That means this is 2Gm1m by r. Due to this here, due to the moon, what will be the potential energy? Gm by r. Okay, so Gm2 small m r by 2, that 2 has gone here, and this will be initially total energy at this point P. And what is the final energy? That is zero. Total final energy will be zero, right? So look, I have to find out VE. So let me just skip this, half m VE here, and on the right hand side I can write 4, sorry, yes, I can write this as G small m by r. Let us take that common. 2 G small m by r common, and this will be m1 plus m2, right? Now further, so this small m I can cancel from both sides. Okay, so what I get? I get v square is equal to 4G by small r and whole into m1 plus m2. This is all right. So what is this? BE escape velocity will be whole square root of 4g by r into m1 plus m2. This is actually the escape velocity. Let me see the options here. 4g by r m1 plus m2. So option B will be the correct answer for this question. Okay, I hope you guys have got this answer. So what was the key concept here? You have to remember two things. One is how to solve the problem, or what, like how to approach the problem. So this kind of problem can be solved. So key points here. One is application of conservation of energy. You have to actually, just by seeing this escape velocity, etc., you can think that I will be applying application of mechanical energy conservation. Okay, conservation. This is one point which is true for any kind of problem related to this escape velocity. And second, in fact, when we have calculated escape velocity, we have used this conservation of principle of conservation of total mechanical energy itself. Second point is that kinetic energy as well as potential energy of an escaped object, that means it has gone to infinity, will be zero, or else will be zero. So these are two key points you have to remember here. Okay, so dear students, we'll just move on to the next problem. Okay, so let us go to the next problem. Okay, so this is again an interesting problem. This problem says a reversible engine has an efficiency eta. A reversible engine has an efficiency eta is equal to 1 by 4. If the temperature of the sink is reduced by 80 degrees centigrade, 58 degrees centigrade, its efficiency becomes double. Calculate the temperature of the sink. I have to find out the temperature of the sink. Okay, so see, this is eta 1 and eta 2 is also given, that is 2 times, that means half. Okay, all right, so calculate the temperature of the sink. See how I can do. See, eta 1 is equal to efficiency formula I know in terms of temperature of the sink, which is written as T2 divided by T1, that is the temperature of the heat reservoir. Okay, hot reservoir, sink, and this is called, I think, source, or the reservoir, heat of hot reservoir, and this is cold reservoir. Temperature of cold reservoir is T2 and T1 is the temperature of the hot reservoir. Okay, so here you look, this is actually 1 by 4, and when, okay, I can actually find out what is T2 by T1 here. T2 by T1 I can find out, so it will be 3 by 4, because you take this way, so 3 by 4. So I have got T2 by T1 is 3 by 4. Now let us see what is eta 2. Eta 2 is half. I'll write that. So I can write this as T2 prime. Now the sink temperature is different, whereas the hot reservoir has got the same temperature. So what is this T prime? T prime is actually T2 minus of 58 degrees centigrade. Okay, minus of this. Okay, so So let us write this as T2 minus 58. Okay. So this eta 2 is half, then 1 minus T2 minus 58 divided by T1. Okay. Now 1 minus T2 by T1, T1 plus 58 by T1, right? So this ratio I know, this is 3 by 4 plus 58 by T1. So from here, see 3 by 4 means, you know, you will get 1 by 4 over here, and here left hand side 1 by 2 is there. I can just take them here. Okay, so this will give you 1 by 4 itself. So what I get from here, I get T1 is equal to 4 into 58. Okay, 4 into 58. This is in Kelvin actually. This is in Kelvin. Now let us do one thing. So I have got T1 is equal to 58 into 4. Now what was T2 actually? T2 was, say, T2 by T1 we had got a ratio, right? T2 by T1 we got a ratio 3 by 4. 3 by 4. So from here I can find out what is T2. T2 will be 3 by 4 into T1, which is this. Okay, let me write once T1. Here I'll write T1, and T1 we have got as 58 into 4. This 4 cancels each other. So what I get, this is 24 and 57. Okay, so this is actually T1. Okay, okay, I'm sorry, this is T2. So T1 we have got, I think this will be in degree centigrade itself, because I have not added anything with this. Okay, if I would have added 273 with this, then it would have been Kelvin, but whatever I am getting, this will be is in actually degree centigrade. Let me check the options. Yes, this will be actually in degree centigrade. So sink temperature will be nearly 174 degrees centigrade. Okay, all right, so this is actually the answer. Okay, I hope you guys have understood this, right? This is very simple problem. Now let us try to solve this problem. Okay, before solving that, let me quickly discuss this problem. Angular momentum of a single particle moving with constant speed along circular path. So suppose a single particle moving in a circular path. So what is the physics over here? In case of uniform circular motion, we know if there is an object which is uh, undergoing circular motion, uniform circular motion, and if the speed of the particle is v, so this will be always along the direction of tangent. Okay, its magnitude remains the same, but its direction changes. That's why we'll get linear acceleration. But what about angular velocity? Angular velocity, that is not going to change actually. That will be always constant. One more thing, look here, the question is angular momentum of a single particle moving with constant speed along circular path. So angular momentum is actually r cross p, if you take in terms of vector, and r is the radius vector here, okay, and p is along the v direction, okay, along the v direction, because p is equal to mv. Let me write it here, mv, okay. See, this p and r both are always actually perpendicular to each other, right? Both are always perpendicular to each other. That means angle between them will be 90 degree, okay. So mvr sine 90 degree, magnitude is fine, but there should be some direction, right? So in which direction the angular momentum will be acting? The angular momentum will be, see, if I just take the right hand thumb rule, according to thumb rule for this case, it will be in the upward direction. This is angular momentum direction, direction of angular momentum in the upward direction if my circular path is in the horizontal plane, right? And this direction, if you take at this point, at this point, at this point, everywhere the direction is not going to change. So the direction of angular momentum is not going to change. That is actually constant. And see, m is constant, speed is constant, and radius also is constant. So the magnitude, so the magnitude and the direction of angular momentum remains constant, okay. Now let us read the options. So angular momentum of a single particle moving with constant speed along circular path remains same in magnitude but changes in direction. This is not true. Direction doesn't change. Changes in magnitude but remains in the same direction. That is also not true. Remains same in magnitude and direction. So option C will be the correct answer for this question. Okay. So dear students, this was non-numerical but conceptual problem. It was really very important problem. Like conceptual understanding is required. Now we'll try to solve another problem. This probably will be the last problem for this session. Okay, so look here, this question is really very important question. This is from collision. A body of mass capital M moving with speed v, let us take this mass to be capital M, which is moving with speed v. Suppose it is moving in the positive x direction, okay, and it's, you see, it collides elastically. It collides elastically with a mass small m. Suppose there is a small m mass over here. It collides with small m mass at rest. So initially it was at rest, okay. After the collision, two masses move at angles theta 1 and theta 2. Let us say this is theta 1 and this is theta 2. So small mass m and this side capital M, okay. for which theta, okay, so we have to find out the largest possible value of the ratio of capital M by small m, for which theta 1 equal to theta 2. Theta 1 and theta 2 will be equal. This one. So this problem, if we try to solve, this is very easy to solve. Actually, we have to apply, since it is collision, we have to apply both the conservation of linear momentum and conservation of speed, kinetic energy. And in this case, we have to consider, since these angles are theta 1 and theta 2, we have to consider both the laws in both the direction, okay, in the x direction and in the y direction, okay. So for theta 1 equal to theta 2, that is, let us say that is theta, we can say that the momentum in the positive x direction will be conserved. So what is that? Linear momentum initially was mv0, right? And that will be, see, this is theta 1 cos theta 1. So this is, suppose, the capital mass going, so mv1 linear momentum, I am actually calculating, capital M collides with v0, right? Let us take that v0, mv0 initial, that will be equal to mv1 cos of theta 1, okay, along the x direction. So I'm actually applying linear momentum along conservation along x direction, positive x. So this will be small m, right? This will be small m cos of theta 2. Let us say the speed on either side will be v1 and v2. That's how I'm just considering. This side it is moving with velocity v1, this as v2. Okay, so this will be mv2 cos of theta 2. Okay. Now along y direction, what will be the initial momentum? That is 0. Final momentum will be, say, mv1 cos of sine of theta 1 minus m2, sorry, this will be small m v2 sine theta 2. Okay, this will be in the this direction, this will be in the upward direction, so they will cancel each other. Okay, from the figure itself you can see that. So m, okay, so this is the thing we have got. These are equal actually. Okay, now from these two equations, so 1 and this is 2, suppose, from here actually we have to solve for M1 and M2 ratio, right? So if we solve these two equations, I'm sorry, somehow I don't have space here. I'm just going to the next page. So from this equation, let me write down here equations. mv0 mv1 cos of theta 1 plus m small m, here small m v2 cos of theta 2, and by the way both are same, so I'll write m v1 plus m v2 cos of theta. So applying conservation law in the vertical direction, we have got mv1 sin theta 1 or sin theta is equal to mv2 sin theta. Okay, all right, so these are two equations. Now if I apply conservation of kinetic energy, then half capital mv square, this is the initial kinetic energy. What will be the final kinetic energy? Half mv1 square plus, okay, v2 square. Now substituting v2 and 0. See, I'll get v1, v2, etc. relations from here. I'll just use them from this equation, and substituting v2 and v0 will get m by small m plus, so this will be cos square 4 cos square theta, which is actually less than 4. Okay, or m by m will be less or equal to 3. So this is the ratio. Okay, so this is the maximum possible ratio. That means, maximum possible ratio will be m by m is equal to 3, such that the angles theta 1 and theta 2 will be equal. Okay, so this was actually the question, and see, the option C will be the correct answer for this question. I'll stop it here for today. Next day we'll continue with other questions from the same set, same shift. Okay, all right, so bye for today. Thank you so much.